Okay, welcome everyone to the last session of the day on linear layer design. And the first talk of the session is about a framework with improved heuristics to optimize low latency implementations of linear layers by Haotian Xi, Xiaotou Fang, and Shengjuan Hu. And Haotian is giving the talk. So the stage is yours.
Thank you. Please. Thanks. Hello. Thanks for the introduction. This is a joint work with Xiutao Feng and Shengyuan Xu. This presentation is divided into 4 parts: the background knowledge, the state-of-art heuristics, our method, and its applications on some matrices. First, the background of this work is lightweight cryptography. It provides symmetric primitives which facilitate secure encryption with low resource costs. And the application scenarios include Internet of Things, wireless sensor networks, and some other devices with limited resource. The metric in terms of hardware implementation includes the circuit area, power consumption, and latency. And there are typically 2 research directions in this work in lightweight cryptography. One is to design new ciphers with lightweight building blocks. And one of the hot topic is to construct lightweight MDS matrices. The second research line is to optimize the implementation of linear and or nonlinear layers of existing ciphers. This work focuses on the circuit area, the latency, and only the linear layers are considered. First, we make it clear the implementation of a linear layer. The linear layer of a cipher is actually a linear Boolean function. It takes input vector X and outputs a vector Y. The Y transpose is calculated by matrix multiplication A times X transpose. And we say the matrix A is actually describes the linear layer, and the matrix is the linear layer. And in the implementation, we use a node vector to define an intermediate value. That is, the node is actually the coefficient vector of the corresponding intermediate value. And the implementation of a linear layer is described as a sequence of nodes. The set of nodes contains all output nodes and satisfies xi equals xj, xor, xk, where jk is smaller than I. That is, all output nodes are computed. It is also called a general implementation of A with XOR gate count C. Note that for an output node such as Y with Hamming weight omega, trivially omega minus 1 XOR gates are needed to generate it. So a trivial implementation of A needs this number of XOR gates. However, since the intermediate nodes can be reused, the XOR gates can be saved in the implementation, and the XOR gate count is related to the circuit area. Here is a small example, a 3x4 matrix A. It has 2 implementations as follows AB. The implementation A only needs 3 XOR gates. And one can say that the nodes X4, X5 can be used as intermediate node. The implementation B needs 4 XOR gates, but it has lower depth, which will be explained later, the depths of the definition of depth. Note that a trivial implementation needs 6 XOR gates. In addition, the definition of implementation graph is useful to describe the implementation. The nodes are actually the nodes in the implementation, and the edges are about the edges. If xi is generated by xj and xk, then there are 2 directed edges from xj, xk to xi. This figure illustrates the 2 implementation graphs of the implementations A and B. Then there's another important metric depth. Given an implementation, the depth of a node in it is defined as the length of the longest path from an input node to it in the corresponding implementation graph, denoted by dt. Actually, it is a simple property that dt1 is equal to the maximum of dt2, dt3 plus 1 if t1 is generated by t2 and t3. Then the depth of the implementation is defined as the maximum depth of all output nodes, denoted by di. The depth of the implementation is related to the latency. Then it comes to the minimum depth. Actually, for each node, it can reach a minimum depth. It is related to its timing weight, and it is easy to see that it can be calculated as this. And then we have the minimum depth of a matrix. The minimum depth of a matrix is the depth that all its implementations can achieve. It is easy to see that the minimum depth equals the maximum depth of all d minimum yi. And this kind of implementation is called a minimum implementation, minimum latency implementation. And in this paper, in this work, we focuses on minimum latency implementations. Then we formalize the SLP and SLPD problem. Given the matrix A, the SLP problem aims to find an implementation of it using the least number of XOR gates. And the SLPD problem differs from it that the goal is to find a minimum latency implementation of it using the least number of XOR gates. Note that the SLP problem over F2 has been proven to be NP-complete. And this paper focuses on the SLPD problem. Then we will introduce some state-of-art heuristics. Up to now, there are typically 3 types of heuristics. The first is forward search, which is represented by variance of the BP algorithm. The second type is the backward search. The third type is the local reoptimization algorithm. First, let's start with the BP algorithm. The BP algorithm involves 2 key parameters, the base set B and the distance vector dist. The base set actually contains all the nodes that has been computed, and the distance vector dist describes the base set, describes the distance from the base set to all output nodes. What's more, the dist I is defined as the minimum number of terms in the base set to generate the output node yi. So it characterizes the distance from the base set to the output nodes. And the main iterative steps of the BP algorithm is to select a new base element generated by 2 nodes in B and add it to B. Then the distance vector is updated. The iterative step can repeat until all the output nodes are generated. Then BP's strategy to choose a new base element is as follows. First, a cost function to minimize is defined as a greedy index to guide the search. It is defined as the sum of all dist I. If there are multiple choices which lead to the same of minimum of the cost function, the tie-breaking rule is to maximize the Euclidean norm of the dist vector. The motivation behind is that in SLP problem, one prefers unbalanced distance vector, since in this toy example, a distance vector like 2, 2, 2, 2 is worse than 1, 1, 4, 2, since 4 XOR gates is necessary for the former case, and while the 3 XOR gates may be possible for the latter case. And there is also a preemptive strategy about the output node. Then there are some innovation points on the variance of the BP algorithm. The RNBP algorithm ensures that every tie-breaking choice is equally possible to explore much more possibilities. The A1 algorithm has a restriction on the choices. The choice of new base elements must reduce the distance to at least one of the nearest targets. That is, at least one distance that is not equal to the minimum must be reduced. The motivation is that the motivation is actually similar to the tie-breaking rule of the BP algorithm. That is, it prefers the unbalanced dist vector. The LSL algorithm then adds a deep depth limit on the base elements, and the dist vector is calculated under the depth limit. So it deals with the SLPD problem. The BFI algorithm focuses on the matrix PAQ, where PQ are permutation matrices. The second type of heuristic is the backward search. It initializes the search from all output nodes by determining how a given node is split. That is, how a node is generated by P and P prime. This process continues until all output nodes are split. All nodes are split into input nodes. The parameter involves a working set omega, a predecessor set P. The working set contains the nodes to be split, and the predecessor nodes contains nodes that is used to split. That is, a parameter S indicates the depth of elements in W, and the nodes in P have depth less than S. So the depth is controlled by this. So the goal of the backward search is to maximize the reuse of predecessor nodes in P to save XOR gates. To achieve this goal, the authors propose a heuristic to randomly choose one splitting operation, which satisfies the rule with the highest priority. The authors developed 5 priority-based rules for splitting nodes. In terms of output nodes, used XOR gates and generated predecessors, and the priority is indicated by the number of rules. Then we move to our new method. Firstly, we propose 2 improved forward search, IBPD and IBPD-MD, based on the BP algorithm. Based on the LSR algorithm, we first made an observation about the depth limit. Actually, in the SLPD problem, the outputs and those with high depths, the output nodes and those with high depths have a less contribution to the other outputs due to the depth limit. But this is not the case in the SLP problem. That is, we do not really prefer unbalanced dist vectors. Otherwise, we prefer some relatively balanced dist vector. Consequently, prioritizing closer outputs has a smaller impact on approaching other outputs and may result in the loss of alternative better pathways that generate the closer outputs. Based on the observation, we propose a new tie-breaking rule of minimizing the Euclidean norm of new dist vector instead of maximizing it. The effect is to reduce all dist i's at a relatively consistent pace. With our new strategy, we form two improved heuristics. The LSL algorithm plus RNBP strategy plus our strategy leads to the IBPT algorithm, and IBPT plus A1 strategy comes the IBPT MD algorithm. The difference is that IBPT MD is better suited for a bit looser depth limit, since the A1 strategy prioritize these output nodes. Then we propose a new framework of combining forward search with backward search, named BPBS. One can say that in the backward search, the current nodes can actually be seen as the output nodes of the forward search. So after each iteration of backward search, the current nodes can be seen as the output nodes of forward search. This framework is a combination of forward search with backward search, and it actually adjusts the search space of forward search and is helpful for it to jump out of local minima. And here are some small remarks on the framework. A modified priority is used. That is, the priority of rule 5 is lifted, and a relaxed steps bound is we have a relaxed depth bound because of the forward search. Finally, we give some applications on some matrices. First, we apply our method to the AS mixed columns. In terms of minimum latency implementations, the previous best record is 102 XOR gates. And our method can find, our improved heuristics can find 101 and 100 XOR gates. And finally, our framework can find a minimum latency implementation with 99 XOR gates. Then we apply our method to many proposed MDS matrices and the matrices used in block ciphers. And for most matrices, we can obtain better results. Following the previous works, we also apply our method to many involutory MDS matrices. Our method generates much better overall indices, such as the minimum XOR gates and the reduced XOR gates. That's all. Thank you for your listening.
Yeah, thanks a lot for your talk. Are there any questions from the audience? I will check if there are any questions online. No. So then I have a question. So you searched for optimal latency, right? So for example, for AES mixed column.
Yes.
So did you also try to slightly increase the latency to say 4 and see if you can get close to the absolute minimum of this 92 XORs, or did you not do it?
Yes. Actually, there are two goals. One is the XOR gate. One is the minimum latency. And actually, if the depth limit is a little bit relaxed, the results may be similar to the SLP problem. That is the only the depth limit is set to the most strict. Maybe this kind of results matters, and otherwise one just ignore the depth limit, and just probe the, just focus on the SLP problem.
Okay, thank you. Okay, so then let's thank the speaker again. Okay, the next talk is about the design of a linear layer optimized for 32-bit bit-sliced implementation by Clara Pernot and Gaëtan Laurent. And Clara is giving the talk. So please.
Okay, so thank you for the introduction. So let's speak about linear layers. So our starting point was the study of the LS designs. So the LS design is a family of cipher that are optimized for bit sliced implementation. And the internal state is the matrix of bits of size S times L. And it's an SPN ciphers. So we have three operations in the run function. So first, there is an S-box layer. So one S-box is applied to each column. So here I just represented one S-box, but the same S-box is applied to each column. Then we have a linear layer. So the linear layer is the composition of the application of the linear layer L one time on each row. And then we have a key addition. So it's just a key addition. So typically, we will have 4 lines on 32 columns. So it will do 128 bits, so it's quite convenient. So in 2001, Vincent Ryman and Johan Damon proposed the white trail strategy. So so they say that we not only require to select the Xbox that have some good cryptographic properties, but we also require to design some linear layers that guarantees a large number of active S-boxes. And to measure the diffusion of the linear layer, we will use the branch number. So the branch number is the sum of the weight of X plus the weight of lambda X on the minimum over all the X. So here is a small example. So we will define the weight of X and the weight of lambda X column by column. Because what is important is that whether the S-boxes are active or passive. So here the weight of X is 7 and the weight of lambda X is 10. So the branch number is exactly the minimum number of active X-boxes on 2 consecutive rounds. So it will allow us to compute some security bounds on the cipher. So the goal is to maximize the branch number. So if we go back to the LS design, in the LS design, the linear layer lambda is made of 4 applications of one linear transformation that operates on 32 bits. And the branch number of the big linear transformation is just equal to the branch number of one 32-bit linear transformation, because we can just choose 3 passive L-boxes and 1 active L-box. And then here in the LS design, the branch number is 12, and it corresponds to the best known code over those size. And then another cipher was proposed. So this cipher is Spook, and in Spook, the linear layer operates is composed of 2 linear layers that operates on 2 32-bit words. And here, for the same reason, the branch number of lambda is the branch number of 1 small linear layer, and the branch number is 16. So it's bigger than in the LS design. So our goal here is to extend this work and to find some linear layers that operate on 3 or 4 32-bit words. And we want some linear layers that have some efficient implementations. So we decided to focus on linear layers that are made of XOR and rotation. So here there is an implementation of the L32-bit S-box, L-box, and it's made of 5 steps of XOR and rotations, and it exactly corresponds to this linear transformation. So this is a circulant matrix. And this linear layer has a branch number 12, so it's the same as in the LS design. And what we can see is that all the circulant matrices can be implemented using Xoron rotations. But the goal is to minimize the number of Xoron rotations. And conversely, the inverse of the one linear layer that is that corresponds to a circulant matrix can also be implemented using Xoron rotations. And here, when I spoke about the branch number, in fact, I spoke about the differential branch number, but there also exists a linear branch number. And here, in our context, both are equal. So here it's the implementation of the LBox of Spook and its inverse. So in input, we have two 32-bit words. Then we have 6 steps of Xoron notations, and we output two 32-bit words. Why 6 steps? Because there is one step corresponds to one rotation and XOR per 32-bit word, so it corresponds to 2 lines in the algorithm. So how did the designers of Spook made to obtain simultaneously an efficient implementation of the LBox and its inverse? They use an algorithm, and the general idea of this algorithm is to find 2 linear layers L1 and L2, such that L1 is equal to the inverse of L2. With L1 and L2, 2 linear layers that have an efficient implementation. So to find such linear layers, they proceed like that. So first, they generate some linear layer using 6 steps of rotation and XOR. Then they compute their branch number. If the branch number is smaller than 16, they just delete the candidates. And then if the branch number is at least 16, they look if they have already found an efficient implementation of the inverse. So there is a table in which they store all the linear layer with their efficient implementation that they have already computed. And if there is a collision between an efficient implementation of L and an efficient implementation of L-1, then we are happy. And if it's not the case, we just add L and its efficient implementation in the table T, and we go back to the step 1, and we iterate this until finding a collision. So our goal was to propose a linear layer over 3 or 4 32-bit words. But we have 2 things to solve. So first is how to compute the branch number of the linear transformation, because if we do that naively, it will require 2 to the 128 operations, so it's infeasible. And secondly, how can we do to find an efficient implementation of both the LBox and its inverse? Because the method that was used in Spook used collisions, and here the search space is too big, so we cannot reuse the same method. So first I will talk about the branch number, and then I will present our solution for the implementation. So let's start by the branch number. So let me remind that the branch number of a linear transformation lambda is the minimum over all non-zero x of the sum of the weight of x plus the weight of lambda x. And this can be seen as the minimal distance of a code with the code words that are the concatenation of x and lambda x for all the x. And as we seen the branch number as the minimal distance of a code, we can just apply algorithm from coding theory. So we apply an information set decoding algorithm to compute the branch number. So this algorithm is derived from an algorithm that was proposed by French in 1962. And it allows to find some non-zero code words with the minimum weights. So it's exactly what we want. And I could also say that this is a probabilistic algorithm. So we will not have a probability exactly 1 of finding the lowest weight word, but we will have a strong confidence in this algorithm if we iterate a sufficient high number of rounds of iterations. So how this algorithm works. So here I just represented a small example of on F2 to the 8th. So it's exactly correspond to one linear layer of 8 bits on one word. And the matrix correspond to the input of L8 at the left and the output on the right. So here, because it's linear, we just need to evaluate the linear transformation on a basis. And then this information set decoding algorithm works as follows. So first, we require to select an information set. So this corresponds to select randomly 8 columns. And we expect that there exists that the lowest weight word has a weight exactly 1 on this information set. And then we will put those 8 columns at the left, and we will do Gaussian reduction. And then we'll just have to look at the weight of each line, because if there is a weight 1 on the information set, it exactly corresponds to 1 line of our matrix. So by doing that like that, we are able to find some low weight words. So it's exactly what we want to do. And more formally, what we can say is that we will assume that there exists a word W of weight small w, and we will find this word W if there is a weight exactly 1 in the information set. So it means that if I choose my information set like this, then we will not find the word. But if I choose my information set like that, then we are sure to find this word by performing our algorithm. So this happened with this probability. And we can also improve this probability by not only expecting a weight 1 in the information set, but also a weight 2. So it corresponds to looking at the weights of the XOR of 2 lines in our matrix. And the probability will increase while the time complexity will remain approximately the same, because the time complexity is dominated by the Gaussian reduction. So we apply this algorithm to our context. So we expect the bench number of 4 32-bit words of a linear transformation that correspond to 4 32-bit words to be 21. So we are looking for a word of weight 20. And if this word exists, we hope to find this by iterating a large number of iteration of our algorithm. So if we iterate 2 to the 25 iteration, and each iteration costs 2 to the 16.8, then the probability of not finding such word, if it exists, is 2 to the minus 604. So it's really, really small. This algorithm is much more efficient than the naive algorithm, because in the naive algorithm, we have it requires a time complexity of 2 to the 128, but here we reduce this to a complexity of 2 to the 41.8. But I must mention here that this is the complexity in the worst case, because it's the complexity when the branch number is only 21. So if we choose a random linear layer and we try to compute its branch number, very often it will take less time than 2 to the 41.8, because we will quickly find a low weight word. So now let's speak about the efficient implementation of the linear layer and its inverse. So first of all, as I previously said, the method that was used in Spook is not feasible here, because the search space is too big, so we are not able to find collisions. But sometimes we don't care about the efficient implementation of the inverse. Like, for example, in the counter mode, we always use the linear layer in only one way. But sometimes we want the implementation, an efficient implementation of the inverse of the linear layer. So we propose to use an heuristic algorithm to find an efficient implementation of the inverse. And first, we try to compute the bench number of some random circulant matrices. So we know that we are able to implement those matrices using XOR annotation, but probably it will cost a 9 number of XOR annotations. But by studying those random circulant matrices, we found that the best branch number is 21. And then our goal is to find some efficient implementation of matrix that have a branch number 21. So first of all, we generate some linear layer that are based on 6 steps of XOR annotations. And then we compute their branch number. If the branch number is not 21, we just delete this candidate. And if the branch number is 21, we then look to an efficient implementation of the inverse by applying an heuristic algorithm. And at the end, we keep the linear layer that are the better, the best implementation for the inverse. So to conclude our results, so we've obtained a linear layer that operate on 3 or 4 32-bit words. And the branch number are respectively 19 and 21. So it increased compared to the branch number of Spook, which was 16. Concerning this column, so it corresponds to the number of steps of XOR rotations. So we can see that our linear layer has the same complexity as the one in Spook, but concerning the implementation of the inverse, our linear transformations are much less efficient than the one in Spook. So in this work, we extend the work that was done in the LS design and in Spook, and we propose a linear layer that operates on 4 32-bit words, and that has a branch number 21, which is higher than the branch number of Spook, which was 16. And we also illustrate the interaction between different fields of cryptography, because we use an algorithm from coding theory to find some linear layers. And that's all.
Yeah, thanks for the talk. Do we have any questions? Okay, let me check the Zoom. No questions here. So I have one. Do you think there is hope to find something even better than this 21? Or so in other words, do you know what is the best upper bound for these dimensions on the branch number?
I think no, because for the code is too big, so we are not able to compute branch. But here, if only consider matrices made by XOR notation, I think there is no better things that our work. But if we are looking for other implementation, not only based on XOR notations, probably we can obtain a better branch number.
Okay. I have another question. So did you try to do some experiments when instantiating this linear layer with some S-box and do some calculations on number of S-boxes over multiple rounds? Or?
No, we only look at the linear layer, yeah.
Okay, so if there are no more questions, then let's thank Clara again. So, and this concludes the day of this. So this concludes this day, and see you all at the dinner then.
So the dinner is at 6:30. Don't forget to bring your badge, and for those with diet restrictions, also the colored cards. Thank you.